Hey everyone, my name is James, and in this video we are going to be looking at controlling and linearizing the dynamics of a water tank. And so the situation we have here is we have a water tank with a hole cut out in the bottom that is letting water out at a rate Q, and that's fixed because the hole can't be plugged. And then the height of the water in the tank, which is denoted by this H, is obviously controlled by how much water is going out and how much water is going into the tank. And how much water that's going into the tank is governed by this pump, and it's pumping water in at a rate U. And so the dynamics of this system are described by this equation we have to the right, which is some constant A times the rate of change of the height plus a constant B times the square root of the height, and that's equal to, this Qi should be a U, and that's equal to the rate of water going into the tank. And so this HO point off to the right, this is going to be the desired height we would like to keep the water at in the tank. And so our eventual goal is going to be designing a controller for the pump that ensures that the water is always kept at 4 meters. Now, if we look at this equation, what we see is we have this square root of the height term, which makes this equation nonlinear. So our first objective is going to be linearizing this equation so that we have a linear model that we can apply our control law to. So continuing on from our last video, the linearization technique we are going to apply is our Taylor series linearization. So from the last video, we had this f of x equals and then our sum of terms, which made the Taylor series expansion. What we're going to do slightly differently in this video is you'll notice that because we have this u term, what we actually have is a nonlinear function with two variables. And so the only difference to the last video is that rather than taking a normal derivative with respect to just x, we're going to take partial derivatives with respect to each term. But otherwise the technique is exactly the same. So what we would have is we would have our f of h and u is equal to f at ho and uo, just like in the last video, but this now has two terms, plus, and then this time we have the partial derivative of f with respect to h evaluated at ho times h minus ho. Whereas in the last video we would have stopped here, we now need the partial derivative of f with respect to u evaluated at uo times u minus uo. And for a proper Taylor series representation of the original function, we could keep adding terms, but since we're trying to linearize, we stop at the first order terms here. And now, whenever I'm given a function like this to linearize, I always approach it in the following order. Now, the first thing I do is I rearrange the function so that our h dot of t is by itself on the left-hand side. There's a couple of reasons for this. The first is we're going to be dealing with equilibrium points, so naturally it makes sense to be dealing when this point here is equal to 0. But the main reason actually stems from the fact that as we go on through the course and we start to get to higher order systems, what we'll find is one of the ways we solve those systems is we break them down into a series of first order equations. And so by rearranging it like this, we actually have a technique that's completely scalable throughout the whole course. So that's what we'll do initially. So we'll say our h of t dot. In fact, as we go forward, understand that these are all time varying, but we're just going to drop the t term. So h dot is equal to, and we'll take this one over to the right hand side, minus b h to the half, which is the same as this, plus u, and both of those are divided by a. And so this equation here is actually our f of h of u. And if you remember back to the definition of an equilibrium in our last video, we actually were saying that the equilibrium is the point that satisfies this system equals 0 with another condition. So this is actually a natural form for us to be working in. So now that we have our system in this form, what we will do is we now need to actually solve for each of these individual terms. So what we can do is we can solve it initially for this one here. So if we were to substitute in our HO and our UO into here, what we would get, we would say f of HO and UO is equal to our minus b on a of HO to the half plus UO on a. And then our second term, so we want to take the partial derivative, so we'll assume this bit's a constant, and we'll just take the derivative of this first part with respect to h. So I'll write d to h, h equals ho, is going to be minus b on a times 1/2, so minus b on 2a times h to minus 1/2. And then when we substitute this back in, we'll multiply it by this term here. And we can do the same thing for this one. So f u equals uo. Sorry, so this is evaluated at our HO point. So this will be HO once we've substituted it back in. And so this one here, again, we hold this one as a constant and we evaluate the derivative of this term. So we get 1 on a. Perfect. So now we have our individual terms. And so what we can do is we can substitute them back into this equation. And so we'll get f of h and u is equal to minus b on a HO to the half plus UO on a plus, although this one has a minus out the front, so minus b on 2a, this is the square root of HO, so let's put that down below as well, times h minus HO, and then plus just this last term here, so let's just add that down here, plus on a u minus uo. And so this has just substituted these three terms back into this equation. I'm just going to rearrange this so it's a little bit nicer to read. Okay, so we have a linearized equation, but it's a bit messy with these h minus HO terms and these u minus UO terms. So what we're going to do in order to clean it up is we're going to define what we'd call a delta state, which is just the difference between these terms. So let's say that delta h is just equal to the difference between h and HO. So the difference between our height and our equilibrium point, and then delta u is going to be the difference between uo. Let's have delta h dot, and that's going to be just h dot, and since HO is a constant, it's just going to be h dot. And so now that we have these terms defined, we can make some substitutions. So remember, this f of h and u is just equal to h dot, which is equal to our delta h dot, and that's equal to minus b on a times HO to the half plus a minus b to a HO, our delta H, plus 1 on A, delta U. And we can clean this up a little bit further. We can take the A back over to the left-hand side, and we actually have a value for this HO. We have this value of 4, which is our desired height, so let's substitute that back in. So we have A delta H dot is equal to minus B, the square root of 4 is 2, so minus 2B, plus UO minus B on 2, again, square root of 4 is 2, so this is actually a 4, delta H plus delta U. And so the only thing we really need to fix up here is this UO term, but that's pretty straightforward to do. What we can do is we can actually say, hey, what happens when this difference goes to 0? So all these delta terms are 0, where we get 0 is equal to minus 2b plus UO minus 0 plus 0. And so UO is equal to plus 2b, and these 2 points must cancel, which we'd expect if we're at an equilibrium. And so our linearized equation will be given by A delta H dot plus B on 4 delta H is equal to delta U. And it's pretty straightforward to verify that this is linear. Suppose we now want to control the system so that we keep the height of the water at 4 meters. Well, in that case, we have to design a controller in order to achieve this. So that means we'll have to design a U that ensures that the height of the water stays at 4 meters based on how fast it's draining out at this rate Q. So there's 2 ways we can do this. The first way would be to treat the system like we have our input U, and then we have our water tank. And from the water tank, we can measure the height of the water. And the only real parameters we have to work with here are the height of the water, which we might measure with some sensor. And as we see that height changing, what we could do is we could either adjust U in order to, like, say we increase the amount of water going into the tank if the height is dropping suddenly, and that'll keep it up. And eventually we can sort of find the right point, but there's a bit of guesswork involved in doing it this way. Although, of course, if we know these parameters A and B, which come from parameters of the flow rate and the actual surface area and things of the tank, then we can calculate that algebraically. But the other way we can sort of approach this control problem is if we have a similar setup, because we'll always have the water tank, and we can measure the height of the water at some time, and again we have water going in, but prior to this point here, we actually put a controller in the pump to control the flow rate. So we might have our controller here. And what we can do is we can feed the height that we're measuring back in as an input of the controller, and we can sum it with some reference value. So the reference value is usually the desired height, or the thing you want. Oops, sorry, that should be a minus. And so the difference between the reference and the height we're at, which we're going to call E, the error, is fed into the controller. And so if the height is greater than what we want, so say the height of the water is 5 meters, then 4 minus 5, this is going to be a -1 value into the controller, and it can do some manipulation and scale it so we get the appropriate flow rate in. So essentially the controller would be designed in such a way that it lowers the amount of water going into the tank. Or alternatively, if the height was, say, at 3 meters, so it's dropping too quickly, then this would give us a positive value of 1, and the controller would manipulate the pump in such a way to increase the flow rate so the height of the water goes up. And so what we'd end up doing is we would have a controller of the form U is equal to K R minus H of T. And this is a pretty standard form for these closed loop controllers at this point in time, where if we were to just have U equals KR, this would be the equivalent of our open loop control. What we could do is we could just have some scaled version here, put in our reference value of 4, scale it any way we need to in order for the pump to sort of get what it needs, because different motors, different pumps and all that sort of thing have different voltages and inputs that they run on, so that'll depend on the model, but essentially it just scales that. And if the water going out of the tank is constant, then we should be able to find some value such that this height becomes non-changing. The problem with this approach is if someone was to, say, punch a second hole in the tank, or thermal conditions were changing and the water was evaporating faster than you're expecting, or if there's any sort of disturbance, our model is no longer reliable and this K value isn't changing. So this system here can't compensate for minor changes like that, or what we'd call perturbations and disturbances. So if a system is really reliable, this is perfectly fine, and we've talked about that in another video. But generally, if you need greater disturbance rejection and a more robust sort of control, then we would go this closed loop approach, which would include this second term, where we feed back a scaled version of the output. So here, to include the K term in this model, we would have the K block here. So our output is getting scaled if it needs to be, and our reference would also go through a K block. And because they're the same value K, well, there's no reason we can't just apply it here instead. And where you apply it is going to depend largely on the limitations of what you can physically implement. But whether or not the block is here or you have two separate with the same value, it's the same thing algebraically. But I really want to emphasize, like, the beauty of this approach here is that our U value is automatically calculated in the closed loop based on the height of the water. We don't need to worry about that. Whereas here, the U value is set by the K, but it doesn't know what the height of the water is. It doesn't care at all. We've had to sort of hope that the water was at our value of 4, set everything up, and then if something largely changes, well, there's no compensation. Whereas this second closed loop system actually looks at the height of the water and adjusts the flow rate accordingly. It's not some fixed rate. So because we have so many variables here for the tank that we don't actually have parameters for, so say the surface area of the tank and certain volumes and things like the output flow rate, let's just, we'll continue with this feedback stabilization trend, but we'll move on to another problem and we'll actually solve that to design the actual controller values. So let's do that now. So now, in order to illustrate the controller design process, let's consider a different system. Let's consider this one we have up here in the top left-hand corner, where we have x dot minus 3x is equal to some input u, and u in this case is going to be the controller that we design. So before we start designing controllers, let's firstly actually find out, is our system stable or unstable? And when we ask that question, what we care about in this case is whether or not the homogeneous system, so if we were to take away that input, is the system naturally stable or unstable? So in order to check that, we can evaluate the eigenvalues or the poles of the system, and they'll give us an idea of whether or not it's stable, and we'll show why once we have them. So thinking back to a first year math course, in order to get those eigenvalues, we can simply let x equal e to the lambda t, and if we substitute that back into this top one here, we get lambda e to the lambda t minus 3 e to the lambda t, this is just the first derivative of this one, is equal to 0 because we're considering the homogeneous system where the input is 0. Collect terms, so the lambda t is equal to 0, and so we can see that our eigenvalue or our pole of the system is equal to positive 3. Now, what does this mean for stability? Well, if we substitute this back into our guess for x, so we have e to the 3t, you should be able to see that as t approaches infinity, or we approach our steady state value, this exponential explodes. And so this value here becomes unboundedly large, and if this was connected to a physical system, say it was governing the rotation of something, we would be spinning out of control. So now that we know it's unstable, let's try and stabilize it. So let's suppose that we want our system to end up at a value of x of 5. And our reference in that case will be 5. So if you consider, back to our last example, if this was our system, we had a u going into the system, we had some scaled value k, and r was the reference of where we would like it to end up. And in this case, we would have our x at the output. And if this was closed loop, we would wrap around down to here. Now, I think let's actually do that in this case. So let's add this one here, subtract our output. So we end up the difference between our reference x and where x actually is. Let's just fill that in so it doesn't look like a line anymore. And this is what we're dealing with for our closed loop system. So this u, if we were to trace these back, our u is equal to k multiplied by r minus x. And this is a pretty standard controller design for closed loop control. And the reason we're not using, in this case, just k times r, so we're not using the open loop control, is that you should be able to verify, actually make u equal k to r, and you'll be able to see that we can't actually adjust these open loop eigenvalues the way we would like if we do that. So this is a good starting point, and you can verify that. So let's substitute that back in to our equations. We have our x dot minus 3x is equal to k, and r in this case we've set as 5, minus x, and if we expand that out, we'll get 5k minus kx. We can bring this term over to the left. What have we got here actually? Plus k minus 3x equal to 5k. And if we were to get the eigenvalues of this system, you would see it is equal to 3 minus k. And if k is equal to 0, lambda is 3, and it's still positive. But for any k greater than 3, this eigenvalue will be in the left half plane. It'll be in the open left half plane, actually, and our system will be completely stable. And so at this point, we can just arbitrarily pick a k that's bigger than 3. So let's pick 10, and we'll put that back in. And so if we do that, our closed loop system is given by plus 10 minus 3, 7x equals 50. And this equation now describes the closed loop dynamics of this system. And so now if we solve this first order ODE, we can see the response of the system as t goes off to infinity. And what we'll see is that our response asymptotically approaches our reference value of 5, but it doesn't actually get there. So in this case, we'll reach 50 over 7, so around 7-ish. And as you increase k, so you pick larger gain values, we can get closer and closer to 5 without ever actually getting exactly to 5. And so if your control objective is simply to stabilize the system, as we've said, any k greater than 3 will achieve that goal. If your goal is to reach the steady state value while having a stable system, you'll need to make your k as large as possible. With the upper limit of k here being whatever physical restrictions are on your system. You can't just have infinite gain or infinite energy applied to your system. There'll be a physical restriction that provides an upper bound on that k, even if there isn't a mathematical restriction. So I actually had a really good question about this, and it was, okay, so we want stability and we want to reach the reference value. What about if we just picked a different value of r, and that would actually allow us to have both? It's a really good question, and in this case, that would probably be fine, but generally we wouldn't do that. And the reason is, as our system gets more and more complicated, it's usually not obvious what that alternate value of r would look like. So what we'd probably do at this point is we would probably move on to a technique like PID, proportional integral and derivative control, and that would give us greater control over that response as we approach the steady state, and we'd be able to find values that allowed us to have both the stability we want and ending up at that value of 5. And that's really the point of a lot of the controllers we design in a control systems course. Once we know we can make our system stable, things like PID controllers, which you'll see in the future, allow us to actually control the shape of that response and the aggressiveness with greater fidelity than simply just saying, hey, the system's stable. And that's important if you're designing something like, say, cruise control, where you don't want the car to suddenly lurch to a stop, or you don't want it to aggressively accelerate at a point that might make the passengers uncomfortable. So thanks for watching, and I'll see you in the next video.